erzählen. So nicht. Что прекрасно. Не, ну у меня вот раз сердце идет.
Ну да.
Ага.
Все нормально.
Да, все.
Так, даже начнем. Okay, so last time we started localizing subcategories. I proved the statement that if we take the quotient by localizing subcategories and the quotient functor preserves the coordinates. And as usual, formulating statements for localizing categories, and there is a standard exercise kind of dualize everything and formulate and prove statement for the for localizing categories. So I'll continue with, for example, the next proposition, I'm going to formulate two statements for localizing and localizing case, and of course it will be proof for the localizing case. So suppose, and as usual, I don't say this explicitly, but if I'm talking about localizing categories, I assume that in the category, with category I work with, there are the products. And for dually for localizing, there are products. So let's consider the situation where we have two translated categories. So C is translated subcategory of D. So translated subcategory. So then first statement is that if you, well, I guess I can say that this is for any x, so for any object x in the category D and any object y from the right orthogonal complement to the subcategory C. So functor, the quotient functor Q, functor Q induces an isomorphism of abelian groups, namely from the home within objects x and y in the category D. There is a, of course, the induced map given by the functor Q to the home in the quotient D dot C between Q of x and Q of y. Well, and since this functor Q doesn't do anything on the objects, there is kind of the standard abuse of notation, and people just for shortness write home D must C between x and y, which is just of course the same. So this functor induces an isomorphism. And of course there is a dual statement for the left orthogonal complement. So now x is in the left orthogonal complement to the C, y is any object in the D, and then both there is the same words. And the functor will be again the same. So I don't want to repeat the formula. So the formula is the same. So you can take any object in the first position, second object in the orthogonal complement, and then there is a isomorphism of homes, or you can do the other way around. You can take the first object from the left orthogonal complement, second object is any object, and then there is again the same isomorphism. So let's show that one is correct, that two is the same. So the proof of so let's take a morphism from Qx to the Qy. So it is presented by some rules. So we can draw so x, G, Y. So here, of course, I assume that F is in the morph C. And this diagram, of course, represents map x to y in the D morph C. So then I take this map F from morph C. So W, F is a map to the x, and complete this map to a distinguished triangle. So there is some object Z, and then there is W shifted by 1. So here, since F within the morph C, I can say that the object Z that I have is in the subcategory C. Perfect C. So to this distinguished triangle, I want to apply home. So y factor home with a fixed second argument, which is just y. So then we'll get the following long exact sequence. So for example, we have home in the D between z and y. This is mapped to the home in the D between x and y. Then there's home in the category D, w, and y. And finally, the last term that I need in this sequence is home in the D between z shifted by -1 and w. Right, I can rewrite this last term in this form. So here,
Why you couldn't rewrite it in this form?
no, because I'm supposed to write z w shifted by 1, but I can move the shift
No,
from
there
the.
should be what?
Why is strange? We apply.
Sorry, that's why, yeah, sure. This is just a silly mistake.
And
Yes.
why z with -1?
Oh, because if I just apply this directly, I'm supposed to write z at the first argument and y shifted by 1.
Ah, yes, okay.
So no, wait, is it correct?
Just add z -1 to
Значит,
the
там дальше должен быть вот именно этот. Нет, вроде то.
Все правильно, да.
Yeah. It's I'm saying to complicate this. This is how you get just by definition if you apply home to the y. Yeah. So next observation that since I take y in the right orthogonal, z is in the subcategory, so this home is 0, and of course by the same reasoning this home is 0 because with the shift is just a again object in the C. So this arrow in the middle is an isomorphism. Hence I can say that there is unique map T in the category D from X to the Y such that T composition with F is equal to the G, right? So G is some map from W to the Y. So this map is induced by the precomposition with the F. So there is since it's an isomorphism, there is only unique such T that this formula holds. So then if I have this formula, I can, for example, write that the Qt is equal to the Q applied to the F inverse Qg.
Why?
Is it right?
It should be B from the right of Q of G.
Yeah. So Q F inverse. Yes, so I have this. Well, but I think I'm more or less I'm approved everything, right? So I need to show that that this map on the homes is an isomorphism. So I start with any map, right? And this map here, I can as well present by that fraction at the end of the computation, right? But for any such fraction, for any element here, I can find a unique map T from X to the Y, such that this map is Q of that T. So that's exactly the isomorphism here. So this finishes the proof of 1, and for 2 it's more or less the same. Okay, so from this proposition I have a corollary. So there will be a bunch of quite simple statements with simple proofs, but together they form a kind of interesting set of observations when we finish this set of simple statements. So of course the corollary is immediate. So if C is a tangent subcategory D,
Excuse me, I don't understand. we prove the isomorphism between O from X to Y in D and in category D quotient by C?
Well, I take any morphism here, right? I present this with this roof.
Yes.
Or equivalently, I can say that I present this with this fraction. So
No, if we take some map from homomorphism in the category of D quotient by C, we have this roof.
yes,
This means we have this roof, and how we construct and we construct some element by here.
yeah. So in other words, I can present the map in the home D mod C by the roof, or I can present this by fraction. We discussed this last time. So that's a fraction with the same roof.
Mhm.
So, but I can see that there is a unique map T, which is an honest map from X to the Y in the category D, such that if I apply Q to that T, I get exactly the same fraction.
Okay, and in another direction, it's okay.
Well, since this such T is unique, well, since the existence means that this is of course subjective, and the uniqueness means that this is actually an isomorphism.
Mhm.
Okay, so suppose I have the situation as before, so then the quotient functor Q induces the fully faithful functor, well, of course, triangulated functor. All the functors that we see are triangulated functors. So, for example, if I use 1, then I'll get the functor from the C right orthogonal. There is an embedding which is of course fully faithful to the D, and then there is the functor Q from the D mod C. So this is fully faithful functor. And dually, for the second part, the functor will be C with the left orthogonal complement, the embedding into D, and then the quotient D mod C. Okay, so these two functors are fully faithful. Okay, next proposition. So as before, I assume that I have a situation that I have a triangle separately. So then the following conditions are equivalent. So the first one is that Y lives in the C right orthogonal complement. And the second one is that for any X in the category D, the map that we discussed just in the previous statement from the home in the category D between X and Y to the home in the D mod C between again X and Y. So I'm using notation. I don't write Q applied to the X and Q applied to the Y, since on the objects this is the same. So this map is an isomorphism. Of course, what we just proved is that one implies two. But this is actually equivalent and equivalent to two more conditions. So 3, for any roof, say with vertex W maps S to the X, map F to the Y. So here it was S is an element of C, as usual. So for any such roof, there is element G in the home in the category D between X and Y, such that GS is equal to the F in the category D. And finally, for every map from Y to the X, which is a map in mod C. Right, so I'm assuming that I have a map in the mod C. So any such map in the mod C is a section. fulfill the secret, so I'm going to call it 1 implies 2, etc. and if 1 implies 1.
What do you mean by intersection?
Well, it's section, what's a sectionomorphism? You have a kind of map, and then there is a section which is a map in other directions, right? The composition is arrayed. So I'm claiming that for any such map, there is a map that goes in other direction, the composition is 1. We will see the explicit formulas of what is a map and what composition, what order is 1 in the proof. So I don't want just to spend too much time on defining this, because it will be clear in the proof. So let's see that. So 1 implies 2, this is about previous proposition, there is nothing to prove here. This is something that we already done. So I've separated that proposition because I wanted to formulate this corollary, which is quite an interesting observation. So now let's show that 2 implies 3. So maybe I can squeeze it here. So 2 implies 3. So I know that there is such an isomorphism, and I want to find the corresponding map, right? So first of all, I can write, since this is an isomorphism, I take this roof, I can say that there is, or maybe there is map G from X to Y such that Q applied to the G is exactly what is Q F Q S inverse. Right? This is because, well, I have a roof, right? So this roof corresponds to this fraction, which is an element here, and there is a unique G that such that Q of G is this fraction, right? But this G actually solves the problem, right? Since I know that in this situation Q induces an isomorphism, well, I can as well say that this is equivalent to the composition G and S equal to the F. So 2 to 3 is quite simple.
Why is it equivalent?
Well, since on the homes this is an isomorphism.
Yes.
So I can, for example, take this, move it here, right? So it will be Q of G, Q of S, this is Q of...
Yeah, but it's, Q is isomorphism on these homes, not
Yeah.
for, and we consider homes from W to Y. No, it's the same. Okay.
Okay, so 3 implies 4. Again, a simple observation. Well, since I know this, right? So what I can take is just take F equal to the identity on the object Y, right? So then the existence of such G means that, so then there is G such that GS is equal to the identity on the Y, which is exactly what I mean that any map is a section. And finally, 4 implies 1. This is where we need to do some computation.
It's strange. Usually a section is something that is on the right.
Well, it is on the right.
For the S
So,
section. Okay.
something S is a section. Okay, so in 4 I know that any map from X to the Y in the more C has a section, and I want to show that Y is in the right orthogonal complement. Right, so in other words, what I want to show is that if I take a map F from C to the Y, where C is in the object in the category C, right? So then this map is actually 0, right? Any map is 0. That would be enough to say that Y is in the right orthogonal complement to the category C. So want to show that F is 0. So take this map F, and of course the standard procedure complete these two distinguished triangles. So I have C, Y, map F. So then there is a map S to some object Z, and then map to the C shifted by 1. So here I claim that the S is in the more C. right? Well, C with a shift is again, of course, object in the category C. So hence I can claim by the definition of more C that S is in the more C. And then by the assumption, I can say that there is a map G such that a composition of the G and S is the identity on the object Y. So let's look at the following diagram. Maybe I don't rewrite this triangle, so I'm using this distinguished triangle and then trivial distinguished triangle with the 0, Y identity on the Y, and then again 0. So then here, of course, on the Y I have identity. From the Z to the Y I have a map G that exists. And since I know that the composition of the G and S is the identity on the Y, I know that this square is commutative. Hence, I can claim that there is a map here making the other square also commutative. But if you take this composition, this is of course just F, and the composition here is just 0. Hence F is 0. That's the end of the proof. Okay, if you want, I can state the dual statement, or maybe I can formulate it as just an exercise. Formulate and prove the analog of the proposition for right orthogonal complement to the left orthogonal complement to the C. Of course, there is a dual statement, and with the more or less the same proof with the inverted arrows. Okay, so now I want to finish this introductory section about localizing subcategories. So I'm going to go over the second section of this chapter, 3.2, and I want to call this localizations. Or maybe colocalizations, well, but everything about colocalizations will be an exercise. So definition. Localization in a triangulated category, say T, is a pair L and eta. So where L is a triangulated and the functor, and eta is trinatural transformation from the identity functor of the category T to the functor L. So this is trinatural transformation. So such that for any object X in the category T, L applied to the component of this natural transformation with the object X is the same as this natural transformation with the component L applied to the X. Well, for shortness of the notation, sometimes I'm going to write L applied as some functor applied to the object without parentheses. It's a little bit short. So, and morphism Lx to the Lx is an isomorphism. Right, so which is of course just this natural transformation.
L looks like projection. L looks like projection.
Well, since I essentially am assuming that L is the same thing as the L squared, but I also assume that it's going to be canonical map from the identity to the L. So I didn't define anything about the algebraic geometry, but in algebraic geometry you have plenty of such examples. For example, you can take a scheme, a closed subscheme, then take the function of the local cohomology with respect to this subscheme. This will be a subfunctor of the identity, but you can take any quotient functor, which means that for any object you have local cohomology of the x embedded into the x, and then there is a quotient. So this quotient is actually an example of the localization in the generic category, say, of x modules with quasi-different cohomology. So there are examples, useful examples of these localizations, but since I separate everything into the category theory and algebraic geometry, I only do these examples later. So at the moment I want to develop just pure categorical theory of such things.
What is triangulated nature of transformation?
It means that this is just the natural transformation of functors, and everything can be used with the sheets. So the precise definition was given in the first lecture. You can find this in the recordings. Okay, so first I'm going to prove lemma. So for any object x in the triangulated category, so the condition that the L of x is isomorphic to 0 is equivalent to the condition that the home in the category D, in the category T between x and the L of y is 0 for any object y in the T. Now let's go in one direction. Let's assume that L of x is 0. Okay. By the definition of the here we need the trinatural transformation, we have the following commutative diagram. The commutative diagram, and now since we simply know that this object in the corner is isomorphic to the 0, right, and this map is an isomorphism, so we have composition of f with such some isomorphism which is a 0 map, hence f is 0. While looking at this diagram, we can conclude that f is 0. And in the other direction, so y yeah, just a second. So in the other direction, what I have, I know that all such homes are equal to 0. So let's take as an object y in the category T, just L applied to the object x. Take this y, right? So then home, the 0 home in the category T, from the x to the L of y, which is in this case L of x. So this is 0, but this is also the same thing as the home in the T from x to the x. So for example, the identity map from x to the x is 0, hence x is 0.
We wanted to prove that Lx is 0.
Mhm.
Then we prove that x is 0.
Mm-hmm.
Let's try.
No, it's true because we say that we have the isomorphism between Lx and LLx, not between LLx and x. So I believe that you should write home from x to Lx, isn't it? On the right hand side. On the right hand side, I think that there is a
Yeah.
homomorphism from X to LX.
Yeah. Thank you.
Yeah, but
Like this. Yes.
and why from it we have the Lx is 0?
Well, I think I can also plug in instead of the x just Lx here, right?
What?
So what if I consider home from the L of x to the LL of x, right? So I know that for any x, for any object x in the category G, this is 0.
No, that's not. No, we don't know this. We know only for x.
Well, then there is something missing here. So anyway, so I want to show, right, so the goal is to show that the home of the Lx to the Lx, this is 0, right? So then what we can rewrite this maybe as what? So I want to rewrite this such that first argument is x and the second argument is L applied to something, right? So okay, can we do this? Say x
Well, the way why we know that homomorphism from Lx to Lx is 0?
We want it.
yeah, we want to show this. If I can show this, I can conclude that the Lx is 0. So then, so here, I want to take this home from the Lx to the Lx and write this as a home where I know that the home is 0. So the first argument is from the x and the second argument is from the image of the functor L. And how we can do this?
I believe it's connected with natural transformation from against map to N. Don't you?
Sure, yeah, well, there is a natural transformation from the Lx to the Lx, which is an isomorphism. Well, but I think we need something like a distinguished triangle. So, for example, let's take x, which is mapped to the Lx, right? So then there is the completion of this thing to a distinguished triangle. So let's call this maybe C, right? So
But we know that all maps from x to Lx is 0.
yeah, so all such maps are 0.
That means that C is Lx. Yes.
Yeah, so C, well, for example, this is in the Lx, maybe in the image of the functor L. But also, I want to say that I want to apply functor L to this distinguished triangle, right? So, and then I'll see, when I apply functor L, I'll get L of x, which is isomorphic to the LL of x. Then there will be L of C. And this is L of x shifted by 1. So, since this is an isomorphism, this is isomorphic to the 0, right?
We don't know that it is an isomorphism because we apply L just to 0. Or we don't
No,
know that.
we know that for any x, this is an isomorphism.
Yes, so we apply L to eta x.
Yeah, so I assume that this is of course the component of the natural transformation, and I'm completing this component to the distinguished triangle. So, okay, so what we see that on one hand L, so one hand C is Lx, on the other hand, if I apply L to this again, I'll get 0, right? So it means that,
Why
Yeah.
C is LX?
oh, because by this assumption, this home is 0. For any, oh, I can plug in, for example, instead of Y, I can plug in X here,
Okay.
right? So then L applied to the C or L applied twice to the object X,
So
right?
you said that I thought if it is 0, then it should be like split the same triangle, so it should be like a direct sum of these two points. And if I have a seam triangle such that they are 0 mapped, then the cone should be a direct sum. Isn't that true?
No, we don't need any distinct triangles. We can take at x, then it is 0 map. Then we apply L and get an isomorphism, but it is also a 0 map because
Yeah,
the function is additive. So an isomorphism is a 0 map, and hence Lx is 0.
So that is not the seam triangle.
Yes, so you're saying that from one hand we know that this map is 0, right?
Yes.
From the other hand, if you apply function L to the 0 map, you get an isomorphism, and that's only possible if the Lx is 0.
Yes.
Yeah, so maybe I just erase this completion to distinguish triangles. So this is 0 map, and this is isomorphism. Right, so hence Lx is isomorphic to 0. Yeah, so it's a simple proof, but it's a little bit different than what I was trying to do. Anyway, so that's the end of this thing. And from the lemma that I just proved, I want to derive a corollary.
Excuse me, can you please say again about the example?
Example in the algebraic geometry, or you can take a simplicity and commutative algebra if you like.
Maybe in algebraic geometry.
Take a reasonable scheme, take a closed subscheme, right? So then there is a function of the local cohomology, right? Well, for example, the right function, you just want to relate categories. Well, this is the standard notation is gamma sub z, right? So this is, if you apply this to say sheaf, then there will be all the sections supported on the closed subscheme z. So that's a clearly subfunctor of the identity, right? Because these sections supported on Z can be embedded into the all sections of the sheaf. And then there is a quotient functor. And the quotient functor is the localization functor.
Thank you.
Now we will return to the local homology later, of course. We will need them for some computation, so we're going to repeat everything with more details. So now I want to derive a corollary from the lemma. So for an object X in the translated category T, the following are equivalent. So the following are equivalent. So three conditions. So first condition is that the X is in the let me just introduce notation what's how I didn't define L. So before this corollary I need L. So the standard notation that I continue to use in this section is the following. I assume that I have some localization. So some localization. And then I define the category L to be just by definition the kernel of this localization. So clearly this L is localized in subcategory. Well, for example, you can use the previous lemma, and so here is a little proof. I don't want to formulate this here as a statement. So if you take a home from the direct sum of the xi's to the L of some y, right? By the properties of the home, you can write this as a product. So this is some over I, product over I, of the homes between x, I, and the L of y, which are, and this is for any y in the T, right? So if all these homes are zeros, then this home from the direct sum is also zero. So that's localizing subcategory, and now I can formulate the corollary, which says that for any vector x in the generated category T, the following are equivalent. So first, x is in the right orthogonal to the L. So 2 is that the x, the component of the natural transformation from the x to the L of x, is an isomorphism. And 3, x is in the image of the functor L, which, of course, this is the essential image, which means by definition that x is isomorphic to the L of y or some y. Some y in the T. So this three conditions I provide. Proof. Let's show that 1 implies 2. So now I do what I've tried to do before. So I take this component of the natural transformation and complete this to a distinguished triangle. So there will be some objects. Let's call this U. So this is the distinguished triangle. So again, to this distinguished triangle, I can apply functor L. This is again a distinguished triangle since the functor is triangulated. But since I know that when I apply L, I'll get an isomorphism, I can conclude that the L of Z is isomorphic to 0. So Z is isomorphic to 0. Or currently, I can say that the Z is an object in the localizing subcategory L. Now let's take S in the localizing category L and apply the home functor with the first argument x to the first distinguished triangle. So then I'll get home from S to the L of x, home from the S to the Z, and home from the S to the X shifted by 1. So first home is 0, right, by the lemma. And the second home is also 0, since we assume that the S is in the L and the X. So where is
How the first one goes from the lemma?
And x is the orthogonal of A.
And what?
so in the lemma we prove that the home between such objects, well, now instead of y I use x, and this can be any object. So this is the case if and only if L of this first object is 0, and I assume this because since S is in the L, and L is defined as the kernel of the localization. So the first home is 0 by the lemma. So maybe let me write this by the previous lemma. And this, for the second home, I want to use the definition, right? So here, I know that x is in the right orthogonal to the L, right? And hence x shifted by 1 is also in the right orthogonal to the L. And S is in the L, so hence this home is 0. So the conclusion is from this computation with the homes, since this home in the middle is also 0, it means that L is in the right orthogonal complement. So Z is in the right orthogonal complement of the L. And also we know that the Z is in the L. So Z is in the intersection of the L with the right orthogonal complement to the L, which is 0. Right, for example, because if you have object in the intersection, in particular, see that the home from Z to the Z is 0, which is only possible for a 0 object. So this Z is 0.
I don't understand why.
Well, because if you have an object that lives in this intersection, you look at the home from Z to the Z, and that is 0, right?
Yes, and what?
And if the homes from the object to the object is 0, then the object is 0.
Ah, okay, I did.
Okay, so what we see is that the Z is actually 0, and it exactly means that the component of the natural transformation in this distinguished triangle is isomorphism. So 1 implies 2. Okay, so how about 2 implies 3? I think this is clear, right? Since this is an isomorphism, this precisely means that X is in the essential image. Clear. And finally, 3 implies 1. This is again just a restatement of the lemma. Okay.
Can you give more details in the implication from 3 to 1?
Hmm?
Because in the limit we fix the first coordinate and change the second, but here we fix the second coordinate and change the first.
No, we actually just take some S from L
Yes.
and say that L of S is equal to 0 by definition of L. And then we consider home from S to X. This equal to home from S to L of Y.
Yes.
Home from S to L of Y equal to 0 since by lemma. Since L of S is equal to 0.
No, yeah, so this is kind of very tautological line of statements. Everything follows from the lemma.
Yeah.
Yeah, but the conclusion that we can also draw from this corollary in terms of some simple formulas is the following, that the object is in the essential image if and only if it's in the right orthogonal complement. So the essential image of the localization is equivalent to the right orthogonal complement right? So, and again, if we return to the lemma, we can also interpret this by such formula. So by the lemma, I can say that the L is precisely the left orthogonal complement to the essential image of the localization. Hence, if I combine these two formulas together, I can see that for the such kernel, I have a formula that the L is equivalent to the L with the right orthogonal complement, and then to the right orthogonal complement I apply the left orthogonal complement. we'll have the probably the most important result about localizations, which is a kind of long statement. So let me suppose that I have L into T, and this is thick subcategory. Of course, everything is calibrated. Let me fix notation. So I is the embedding of the L to the category T. Then there is an embedding of very faithful functor from the right orthogonal complement. So J is the embedding of the right orthogonal complement to the T. And functor Q is the standard quotient functor from the T to the T quotient by the subcategory L. So the Grothendieck quotient. Then with this notation, the following conditions are equivalent. There will be 6 conditions. So first is that there is a localization L from T to T, so the functor, such that the kernel of this localization is precisely L. So the second condition is that the functor Q has right adjoint. So Q has a right adjoint. So 3, composition of the Q and J is an equivalence of categories. Equivalence of triangulated categories. 4, functor J has left adjoint. Functor J has left adjoint, and additionally, I have the property that I proved before, so that the L coincide with the 2 orthogonals. So condition 5 is that the functor I has a right adjoint. And 6, for any object M in the triangulated category T, I can write a distinguished triangle. So there is a distinguished triangle with the object NM and the BM. So there's kind of M is given, and I can find 2 other objects, NM and BM. So that there is a NM with a shift. Well, such that this object M, depending on M, is in the subcategory L, and the B with the index M is in the right orthogonal. So these 6 conditions are equivalent. So the proof will be, of course, kind of long because, well, there are a lot of implications that I'm going to show. So the plan for the proof is I'm going to form 1 to 2, from 2 to 3, etc., and finally from 6 back to 1. So to basically. Yeah, and maybe before I start with the proof, I can say why this is an interesting statement. Well, we saw that there is a problem that this T modulo L could potentially have homes which are not sets but just classes. And since we know condition 3, that this is an equivalence of categories, we can realize the quotient category as a subcategory inside T. For example, if for T we know that the homes form sets, so then for the quotient it will follow from 3. So why this is theoretically quite an important statement, and this is how kind of the one of the ingredients to show that the derived category for a Grothendieck category has small home sets, small homes.
Yes, and everything works if we consider not right orthogonal to L, but left orthogonal.
Yes, of course there is a kind of theorem with the prime, with everything dualized. Okay, so let's show that 1 implies 2. So here we have functor L, which is functor from T to T. So then there is a quotient functor Q, And I claim that since L is in the kernel of L, well, in fact, this is just L, this is just a definition of the kernel, but for using the universal property, it's enough to have only the embedding, so there is a functor R from the quotient to the category T. So this is by the universal property.
What is L? Well, L small.
Well, in the condition 1, I assuming that there is localization.
There is.
Yeah, and I want to show that Q has right adjoint. So by the universal of property, there is functor R, and so maybe let me write this as a formula. So there is R, which is a functor from the quotient category back to the category, and the composition of the R and Q is L. So the goal is to show that actually this is the right adjoint. So I want to show that Q has right adjoint, which is exactly R. So, and moreover, I want to say that the unit of the adjunction is the map from the 1 to the composition RL, and this in this case, this is just the localization. Sorry, RQ. Okay, so let's take this eta sub x, which is the component of the natural transformation from the x to the L of x. So this is in the more L, right? By the same argument that we've done before, right? You complete this to a distinguished triangle, you apply functor L again, you'll see that this third object will be in the kernel of L. So this is in the more L. The proof is as before. So if this is in the more L, I can say that the Q applied to this eta sub x is an isomorphism. Or any object x in the category T. So given F, which is a map from the x to the Ry, and since Q doesn't do anything with the objects, I can just as well identify this Ry with the localization applied to the y. So given map F, I want to define map G from the Q of x to the y. So this is in the quotient category in the T modulo L. So
Eta x is an isomorphism. Y taken from eta x is an isomorphism.
well, because we saw this more or less by the construction of the localization that any morphism in the more subcategory becoming isomorphism in the quotient category. Okay, so given F, I define G, well, just by the simple formula. So for the G, I can write the fraction. So G is the Q eta sub y inverse Q of F. So this is of course represented by the roof. Let me also, for completeness, draw a roof. So there is X, there is a map F from the L Y, then there is Y, and there is eta sub Y. So for any F, we constructed and the F was from if you imagine this is in the home from the X to the RY, and now I constructed map from the home, which is the Q of X, or I can write as well the Q of Y, but since I don't do anything, I just decided to write like here, so it's clear that this is what I need by the adjunction. So in this proof, I'm going to give you constructions how you can go from one set of data to another set of data, but I'm going to skip some details. So here, for example, you can check that G is unique morphism. And when I'm saying that you can check it, usually it's quite simple to check. I just don't want to spend time on this, otherwise it will be a very long proof. So G is the unique morphism in the quotient category for which the following diagrams commutes. So I have x, I have eta sub x to the r cube of x. So here r applied to the map G. This is r sub y, and this is so indeed what we proved is that the eta is the unit of the adjunction. Okay, so I need to erase the statement, unfortunately. Okay, so prove that 2 implies 3. So in the true, it is given to me that the Q is right adjoint, and I want to show that the composition of the Q and J is an equivalence of categories. So first of all, we already know that the composition of the Q and J is fully faithful, right? I proved this today at the beginning of the lecture. So we want to show, the goal is to show that the composition is essentially surjective. And I know that there is a right adjoint to the Q. I'm going to denote this again by R. So let's do the computation. So take any object X in the triangle category T. If you
Excuse me, want to show that Q and G is equivalence of category.
yes,
What does it mean? AS?
essentially surjective. An equivalence, a factor is an equivalence of categories if and only if it is fully faithful and essentially surjective.
And for faithful, we know by previous term.
Yeah, I think this was the first statement that I proved today,
Yes.
and further away from that level.
Mhm.
So, for any object X, I want to look at the home of the category T from the X to the R to say Y, right? So, this is equivalent to the home, isomorphic to the home in the quotient category by the adjunction Q X Q Y. Alright? Oh, sorry, I don't want to take any object in the T, I want to take object in the L. Sorry. Let's take an X, which is object in the set category. So then the Q of X is 0, right? So hence this whole home is 0. And then it means that if I apply functor R to the quotient category, then the image of this functor is in the right orthogonal to the set category L. So that's the conclusion of this computation. So the computation is kind of just one step. I do the adjunction, and since I know that X is in the L, it is 0 object in the quotient by the L. Okay. So R maps the quotient category to the right orthogonal. So then let's look at the home in the quotient category between the Ux and the Qry. Right? Again, by using the first lemma of today's lecture, I can say that this home is isomorphic to the home in the category T, where I keep object X and write Ry. And then by the adjunction, I can rewrite this again as the home in the quotient category between the objects Q of X and Y.
What is X and Y here?
Hmm?
what are X and Y here?
No, just the objects, so X, so this is true for any X in the T, and any Y, well, I can write this in the T mod L, but the objects are the same, so any Y in the T mod L. So we have this isomorphism
Why have the first isomorphism?
by the first level of today's lecture.
And the fact that R of T of a factor of L.
Yeah, by this fact and applying the first level. Okay, and it is also, since this is just the computation by the adjunction, we can, for example, now apply the Unitas lemma, right, in the category T modulo L. And since by the Unitas lemma we will get the isomorphism, so we view our Y mapped to the Y, and this is the isomorphism. So this is the isomorphism, and also since what I do is just the adjunction, this is the map is just the epsilon sub Y, so this is the co-unit of the adjunction. Co-unit of the adjunction, and the co-unit of the adjunction is the isomorphism. So, and that is true for any Y in the quotient category. Hence, we can conclude that the composition of the Q and J is essential surjective. Wait. Okay, so this finished the proof that 2 implies 3. Now, let's prove that 3.
Can we conclude that Q of J is essentially surjective?
Well, for example, by looking at this formula, right, you can take any object in the quotient category, and you can represent this object as the Q applied to some object which is R of Y, which is in the here, right? But if this is in the here, this is in the image of the function J. Okay. So we have 10 minutes, and I think we can do.
How we get it co-unit is an isomorphism?
That this is an isomorphism
Yes.
by the unit lemma. So we have home, with the first argument is the same, right?
Yes.
So
Or yes.
by the unit lemma, we have an isomorphism between this object and this object, but also by this computation it's clear that this isomorphism is precisely the co-unit of the adjunction. Okay, so 3 implies 4. So in the 3, let me remind you, we know that the composition of the Q and J is the equivalence of categories, and the goal is to construct the left adjoint to the function J, and also there is this identity for the subcategory L. So we're going to do separately into 2 steps. So first of all, since here I know that the composition of the Q and J is an equivalence of categories, so this is an equivalence of categories. There is functor going in the other direction in this equivalence. So functor, let me call this little r, from the quotient of the category T modulo L back to the right orthogonal of the L, such that the composition of the R, Q, and J is the identity, and composition in the other order, so Q, J, and R is also the identity.
What do you mean when you write equals to identity? It just equals?
No, of course, whenever I say equals, I mean,
We will.
but here naturally isomorphic. So there's natural transformation, which is an isomorphism in every component. Well, this is the definition of equivalence of categories, right? Equivalence of categories, it means that function in one direction, function in the other direction. If I take a composition, then this is naturally equivalent to the identity, composition are there, or also natural equivalent to the identity.
Yes, I'm just concerned that we have these natural transformations to identity and we ignore them.
No, they are here. I'm just a little bit abusing notation by saying that they are equal. I assume that there are natural transformations, one and the other, and there's a natural transformation such that all the components are isomorphisms.
Okay.
So the goal, so what I want to show is that the composition of the R and Q is the left adjoint functor of the functor G. Okay, so one of the claims I want to show is that the J has left adjoint. So I claim that the left adjoint is the RQ. Okay, so I want to show that, well, first of all, if I take the isomorphism from the object X to the Q, J, and R of X, so there is such an isomorphism in the T modulo L. So this is the image of the map eta sub x from the x to the j r of x in T. Right? And this is because since j r of x, well, just more or less by definition of the j, this is an object in the L right orthogonal, and again by the first lemma.
Then why we say that it's eta of x?
Well, because the plan is to show that this is a unit of the adjunction. And well, first of all, it is clear. So more morphisms eta sub x form a natural transformation since we started with the natural transformation. So natural transformation from the identity functor on the T to the JR, and I can also add Q because Q doesn't do anything on the object. Okay, so and then for the next computation I want to take X to be an object in the category T, and I want to take object Y in the right orthogonal of the L. So then for such two objects, if I look at the home in the category which is right orthogonal to the L between R, Q, up Y to the X and object Y, well, I can first of all rewrite this as a home in the quotient category between Q, R, Q, Y to the X and the Q, Y.
Why this?
Well, that is because we know that Q and J is an equivalence of categories, so these two objects are kind of in the image of the J. So when I apply Q to them, this functor is fully faithful.
Ah, okay.
Just from the lemma, the first lemma of the lecture.
Yeah, by the
Hey.
definition of the fields of categories.
Yeah, or you can say this is by the lemma again since the
No, because here we have L orthogonal.
Yes. Yes.
It's not the same as
no. Oh, anyway, so the first explanation works.
And we need to prove that.
Well, since we know that it's home in L orthogonal, well, Well, home J is full faithful.
Yes.
So you can just apply J to home in a orthogonal, get home in tau, and then apply the first lemma. It works.
I think it's just because QG includes.
Okay.
Oh, okay, yes. We need to apply it. Yes, okay.
Actually, yeah, okay. It works.
Yeah, it works. And the second step is kind of trivial, but a little bit more interesting. So I can write home in the quotient. But now, instead of the composition of the Q, R, and Q, I'm writing Q, J, R, Q, X, right? I just insert one additional J into the formula. And this works, of course, since if I look at the object R, Q, X, then this is in the right orthogonal already to the L, right? Since I apply function J, it didn't change anything. So this is this home. Now there are formulas for, right? So here I want the composition. So what there are two formulas that three compositions are the same as the identity. So here, for example, what we can apply, I can, for example, take this one, composition of the Q, J, and R is the identity. So the composition of these three functors is the identity, and this is just home in the quotient category, T modulo L, between Q of X and the Q of Y. Right? So finally, this home is the same as the home in the category T between object X and the J applied to the Y. So by the assumption, so it went from 3 to 4. So the composition of the Q and J is the equivalence of categories. Yeah, and here, again, we're using something like the first lemma. Right, so this object J of Y is in the right orthogonal complement to the L.
What you need it's at the X for?
Well, and now the simple exercise is to see that, well, we have the beginning of the computation, this home, and we have the end of the computation, this home. So,
Excuse me, nevertheless, I don't understand the first isomorphism. So we have A orthogonal, and then we have to apply the function J. Okay, we apply it, and we have this isomorphism to home in tau from RQX to Y. Isn't it?
well, by the assumption, I'm writing home in the right orthogonal, right? But I can as well just write home in the T. This is the same home.
As we say that J is fully faithful.
J is fully faithful by the definition, yes.
So it is equivalent to say that this home is in tau.
Yes, of course.
And then we
Yeah.
believe. Okay, thank
Yes. Yeah. So, but now we look at the beginning of the computation and the end of the computation. So we can see this kind of the adjunction of the between the two functors, right? And what I'm leaving you to check is that this isomorphism. Just let me finish this sentence. So is defined by decomposing with the eta. So just a little bit more careful analysis. What you just use here some trivial steps and kind of the junction is the only possibility how this thing can be defined as a composition with the eta. So the question was why the last isomorphism
Yes.
is well,
Yes, it's the first level.
yeah, it's the first lemma. Well, just because again, because the reason is I have this home in the quotient, right? And the second argument in this home is in the right orthogonal. So I can as well think about this home as the home in the original category, right? And just because I want an adjunction, I can, well, write y here. But to be a little bit more precise and see formula for the adjunction, I just write j of y.
Why, by the way, why you write J of why not Y?
Because if I skip this j, it doesn't change anything.
Because Y is
And I'm writing this j to see the adjunction. Okay. So it looks like I'm out of the time, so I proved the first part, and there's also, remember, and in 4 there is a second condition about the left and right orthogonal, so maybe let me give us a little break.
we need to prove that this method joint
So we need also to prove that if you take the right orthogonal and the left orthogonal to the L, it's again L. This is part of the condition 4.
мы в четвертом должны были показать, что J имеет левые сопряженные.
Да, это мы показали.
Да.
Там есть еще второе условие.
Читают мои письма, но нет,
Просто именно забудьте про схему. Там L это будет категория явки с носителями на этот подсхем или нет? И тогда как может Павлов интерпретировать с точки зрения?
Обычно по схеме мы понятно, как звук А. Это значит просто...
Сейчас я отвечу. Фактор это будет, в триангулярном случае это будет о X-модуле с корректным имя на подсхеме, на схеме U, где будет вкрытая подсхема выполнения C.
Логично.
И спросите, а там сам хочет просто по сумму?
Да.
У меня вроде бы нет.
Буквально вчера вечером.
Вроде должен быть. Я вчера вечером сделал рассылку.
Рассылку ты...
Ну, как, я когда знаю, что эти самые имейлы, я могу просто там типа добавить список имейлов и пригласить всех студентов. Я вчера вечером это сделал. То есть должно было прийти письмо, и там приложить нужный знак.
Наверное, если она пригласили, автоматически не попал. Ну, я так думаю, что, наверное, надо донести это письмо и писать.
Ну да. Надо было буквально вчера вечером.
Спасибо.
Александр Борисович, вы не могли, пожалуйста, сказать, какой у вас почта?
Спасибо.
Да, кстати, а там в домашке вот A и B, это же считается за 1 балл? Ну,
Да.
Каждый пункт 1 балл.
Ну да.
Отлично.
Нет, все
Нет?
пункты 1 балл.
Но это неправильно.
Нет, это я скажу. Ну, потому что там, эти задачи с пунктами нереально простые.
Ну да, но там есть 5-я и 7-я задача, которую я бы лично не хотел решать. А там всего 10 задач.
Именно по этой причине там ровно 10 задач.
Чего вот это ужас?
А сколько надо решить?
10?
Из 10?
Да.
То есть все надо решить?
Не, ну надо решить 40 за 4 ассайнмента.
Так всего их будет 40?
И всего будет, скорее всего, больше задач.
Больше, но просто проблема в том, что у меня не очень много задач после по этому предмету. Поэтому я могу попытаться сделать 11, 12, но вряд ли сильно больше.
в виду вот в первом аргументе изоморфизм из x у g от x. Это образ это x, потому что g от x в L ортогонально.
Да.
У нас ведь вот там просто какой-то изоморфизм между у g от x и x. То есть, что тут имеется в виду, вот в этой?
Нет, если имеется в виду, что вот у меня есть вот этот изоморфизм,
Да.
он дан таким естественным преобразованием.
Да.
Вот я как бы пишу компоненту этого естественного преобразования для объекта x.
Да, но она какая-то неизвестная нам.
Ну какая-то она есть, да. Мы знаем, что она существует.
Да. А тут что написано?
Ну, тут написано, что, соответственно, это что там происходит по фактор категории, да?
Да.
Соответственно, и у нас второй объект, JR, да, очевидно,
Да.
находится в правом ортогонале.
Да.
Понимаете, снова смотрим на первую, когда что-то не сказано, значит, по первой линии.
Да.
Значит, мы смотрим на первую линию и мы понимаем,
Поэтому на образ какого-то
да,
морфизма.
какого настоящего морфизма,
Да.
этот настоящий морфизм будет обозначаться и когда
то есть это определение.
это определение
Да.
и с индексом x, и после этого проявляется, что это как раз и есть единица
Да.
сопряженности.
Да. Да, то есть мы определяем это x как прообраз вот этого морфизма, и да, оказано это единица. Спасибо.
Ну что, ты погнал? Я погнала. Ты чё? А он съехал. На моменте. Короче, сказали удостоверение.
Тут получается вот, где написано, что морфизм это формирует естественное преобразование, там не должно быть.
Ну,
Или тут...
здесь проблема в том, что всякие вот эти QG я могу вставлять,
Да.
не вставлять,
Да.
они...
Да. То здесь имеется в виду тут в Q от X. Можно было бы приписать.
Да, здесь можно между R и X вставить,
Да.
но тогда формально как бы говорят, что у нас R есть определен, то есть
Да.
ты должен был, что там было написано, да.
Можно в этих задачах скинуть ссылку на рекламный точечно страницы, в которых доказывается TR1, TR2, TR3, TR4. Думаешь, там не все доказываются. TR1 готов сам доказать.
Нет, там интересно только 3-4, конечно, все остальные.
Они там доказываются.
Можете почитать, разобраться.
Я это уже делал в своей жизни. Мне хватило. Но это не причина моего нехотения делать это.
Нет,
Повторять.
можете не делать, зато потом компенсируете.
Ну, молодец.
Следующий
Я не хочу этого.
Нет, следующих листочков решать 11 задач, 12 задач.
Ну, я этого тоже не хочу.
Будут такие опции? Там будут опции с 11 задачами?
Я постараюсь сделать. Ну, просто я говорю, не очень много задач. Но я знаю всякие хорошие задачи, которые, не знаю, можно придумать, что это можно все равно не написать вообще. Такие приятные. Можно будет добавить. Okay, so to finish this implication that 3 implies 4, we also need to check the conditions about the left and right orthogonal complements of the category L. So first of all, for any category L, the following is clear. So clearly, L is contained in the two orthogonal complements. This just follows directly from the definition of orthogonal complements. So one inclusion they always have. So we really need to show that there is an inclusion in the other direction. So let's take X to be an object in the left and right orthogonal. Well, I guess I need to say right and then left. And Y is just some object in the category T. So then for these two objects, we again compute some home. So the home, I start with the home in the quotient category between the Q of X and the Q of Y. So then this home, since R is an equivalence of categories, I can rewrite as the home No, I don't. Wait just a second. Yeah. So R is an equivalence of categories. So yeah, I can write this as the home. Oh, I don't have time here. So I don't have space here. So
Ой.
Да.
yeah. So continue here. So this is the home in the L with the right orthogonal R Q X R Q Y. Right? R is an equivalence of categories, so I have this home. So then I can use the adjunction that I already proved, that the RQ is the left adjoint to the J, and rewrite this as the home in the category T between X and J R Q Y. So here for this thing I use the adjunction between the RQ and the J. Okay. Now X is in this left orthogonal complement, so I claim that this last home is 0, and this is because if I look at the J, R, Q, Y, this is, again, more or less by the definition of J, is in the L right orthogonal. Okay, so this home is 0. So this home is 0. And from this, I want to conclude that Q of the X is isomorphic to 0. And why this is so? Yeah, so by Unetta.
Yeah, we know that every object of T quotient by L is some Q of Y. Since Q on the object is just doesn't do anything.
But if we apply J and there, it's not all.
Yeah, but we say that the first one, homomorphism from Q of X to Q of Y, is equal to 0. And we say that we compute all homes from Q of X to any object in T quotient to X.
Yeah, since this is a 0 function, it's only possible for a 0 object. Yeah, so the Q of X is 0. So in other words, another way to formulate this is to say that the X is in the L. And for this application, I use the assumption that the category L is thick. Then I know that everything in the kernel of the Q is the same as an object in the category with respect to which I take a quotient. So X is in the L, and that's what I want, right? I started with the X from the right-hand side, and I showed that this is in the left-hand side. So this finishes the proof that 3 implies 4. So now 4 implies 5. Which I think is the most important proof. This actually shows what's going on in this statement. Okay, so in the 4, I have that the functor J has left adjoint, and we have this identity equivalence between the two subcategories. Now I want to show that functor I, which is the vehicle, the L into the T, has a right adjoint. So let me fix some notation. So let J prime be left adjoint to the J. So it's a functor. So J prime is a functor from the T to the L right orthogonal. So let's take Y to be an object in the right orthogonal to the L, and again do computation with homes. So we have home T J prime X, and then J Y. So this I can rewrite as the home in the category L with the right orthogonal, and I just drop the J. So it will be J prime X and Y. So J is the identical of the category L with the right orthogonal to the T, and this is really fully faithful by the definition. So this I can just drop, and I can use the adjunction. So this will be the home in the category T between X and the J, which is applied to the object Y. So I have this computation, and by exactly the same reasoning, I can now add shifts and have an isomorphism between homes, where instead of X, I take X shifted by. Since I'm going to use in a minute this two isomorphism, I want to write them explicitly. So this will be home in the T, X shifted by 1. Or the same, but instead of X, you take X shifted by 1. So let's take a distinguished triangle. I have X. Then there is a component of the natural transformation, which is the unit of the adjunction between J and J prime. So there is a J prime X. And we can take conclusion to a distinguished triangle. Let's call this object N sub X. And the map W sub X to the X shifted by 1. So that's a distinguished triangle. And to this distinguished triangle, I want to apply home with the second argument being j of some object y. So y is just an L object in the right orthogonal to the Okay. So when we do this, and apply this home, we will see that this home will induce an isomorphism, right? So there will be home, for example, from the x to this j, right? And on the homes, this will be an isomorphism. Do I need to write this? Because I want to make a conclusion that when I apply home by this previous computation, I'll get that the home in the category T from the n sub x to the j of y will be 0. Is that clear? I apply home, I'll get a long exact sequence, but home bit from this object to the j of y and home from this object to the j of y are isomorphisms. So I'll get an isomorphism, and then on the next step I'll also get an isomorphism. So this home has to be 0.
What will be isomorphisms?
Okay, so I guess I need to write this. So I'll get home from the x to the j of y. Then this is mapped. This is contravariant function. So this is another order. So I start now from the right. So this is contravariant. There will be home from the x to the j of y, right? So then there will be home from the j prime x to the j of y, right? So so if I have a map to the composition is in this direction, right? No, wait. So then there will be home from the n sub x to the j of y, right? But now, by my computation, I know that this is an isomorphism, right? So on the next step, I'll get the same, but with the shift by 1. So there will be home with the x shifted by 1, and then the j of y. And the same here, but this will be again the isomorphism by this second line of the previous computation. So then I'll get an isomorphism and another isomorphism. So the conclusion is that this object in the middle is necessarily isomorphic to 0. So that's an object isomorphic to 0, and equivalently I can say that the object n sub x is an object in the left orthogonal to the right orthogonal, which is, by our assumption, the same as the category L. So Lx is in the L, in the distinguished triangle. Okay, so I want to continue computation here. So suppose I have a map from the x to the y. So then I have two distinguished triangles. I have x, j prime x, then there is nx, and the x with the shift, and the same for the y. So here the morphism is of course j prime, which I apply to the f. So I want to show, and this is f shifted by 1. I want to show that there is a unique map here on the nx to the ny. And to do this, I can, for example, apply home from the nx to the second distinguished triangle. So then I'll get home from the nx to the j prime y, which is mapped to the home nx and y, and this is mapped to the home nx y with a shift. Okay, so this home is 0, right? Since I know that nx is in the L, and this is of course in the right orthogonal to the L, so this home is 0. But it means that if I look at the map from the nx to the y shifted by 1, which is just this map, right? So there is a unique map making this diagram commutative. So there is a unique map n with the index f. So since this map is unique, I can define a functor. So we define functor I with a prime. So that's a functor from the translate category T to the subcategory L, which is the right adjoint to the embedding. So by definition, on the objects I prime on the object X, so this is nx shifted by 1, and I prime on the morphism F is defined as the n sub F, and again with a shift by 1. So then,
NF.
hmm?
Oh, it's
in F, the map I just defined.
I have a question. How did we define nx? As a column, right?
Yes.
And column in general is not factorial. But so we just computed it and everything. We just defined both. Okay.
Yes. So in this case, the morphism is unique. It has to be defined as functor.
Yeah, and form is unique after isomorphism.
Okay. And now, also with this functor, I want to define the counit of the adjunction. So the epsilon, let's call this epsilon prime. So this is the from I composition with the I prime to the identity functor. And again, this is just by definition. So epsilon prime component for object X. So by definition, this is minus W sub X shifted by 1. So I shifted everything by 1. So, and I claim that this is counit of adjunction. And the reason why I decided to need to shift this everything by 1 to get the correct distinguished triangle without shifts after I define everything. So the distinguished triangle is the following. I have I prime applied to the X, then there is the counit of the adjunction for the X, so this is a map to the.
Excuse me, can you explain this? What does it mean? Counit. Counit.
Counit?
Mhm.
It's just part of the definition of the adjunction. If you have an adjunction functors,
Yeah.
you have the composition of such functors which is mapped to the identity.
Mhm.
There is a unit of the adjunction which is 1 to the composition and the counit. Okay, so here I have a distinguished triangle, so this is given by the counit of the adjunction, and after this I'll get eta sub x, which I defined before. Did I define it before? I don't think so. So I need to define this eta sub x. So this is, maybe I scale it here. So eta sub x is the map that I used from the very beginning. So this is the map from the x to the j prime x. So the unit of the adjunction for the functors j and j prime. So since I have this adjunction, I always have this map, and moreover I use this map here, so I can call this component eta sub x in this first distinguished triangle. So j prime x, and then I'll have I prime x with a shift by 1. So I have this new distinguished triangle, which is
question. Why we have this morphism here epsilon x prime, and why the co-kernel this map is j prime x?
well, first of all, there are no kernels. This is
No,
translated.
like co-kernel.
Well, this is the definition.
I
So
don't know how to call this object such that it's the unique object for the morphism of x to y.
well, sometimes people abuse notation, call this cone of the map.
Oh, but it's cool.
Yeah, but so this is the definition. So this is why we have this map, because I define this explicitly, right? And then we have this kind of new distinguished triangle, which is not really new. It's exactly the same distinguished triangle as here, which is just the same distinguished triangles, but rotated. So this is the eta sub x, right? So then we'll get the next map, and then there will be the next map, which will be exactly the w sub x, which is here. So it's exactly the same distinguished triangle, but now with a different notation. And I think for me this is the key explanation of this whole statement. What's going on? What we have here is that we have the situation, well, in any of the 6 equivalent statements, we kind of have some part of the data, but not all the data. And all the data includes kind of the right adjoint for the embedding and the left adjoint for the embedding of the orthogonal. And if you have these two embeddings, we can always write such distinguished triangles. We can kind of decompose object X into the object in the L and object in the right orthogonal of the L. So that's the whole point to do this theory, so that we have such distinguished triangles.
Yeah, and why I prime is right orthogonal to I? Right.
That's the assumption of what I'm proving. So this is assumption in the condition 4.
No. Assumption in condition 4 is for J prime.
Yeah, J prime is the left orthogonal, yes.
Yeah, and we need to prove that I prime is right orthogonal.
Yeah, we will do this in a minute. Yeah. Okay, so we have this new old distinguished triangle, and to this distinguished triangle, I want to apply Hom. So arguments are always the same. Write some distinguished triangles, apply corresponding Homs, which give us something interesting. So for this Hom, first object is IT, where T is just something from the subcategory L. So then I'll get Hom IT from the to the j prime x shifted by 1. So then this is mapped to the Hom IT I prime x, Hom IT x, and finally Hom IT j prime x. Okay, so I claim that these two Homs in the beginning and at the end are 0. Well, that is because I'm computing a Hom from the object in the L and object from the right orthogonal to the L. So these two Homs are 0. And hence, I have an isomorphism for the Homs in the middle. So, in other words, I can say that for any map alpha from the IT to the X, there is a unique Q, map Q, from the T to the I prime X. Right, of course, this Hom, where I have two I's, I can drop the I because I is fully faithful embedding. So there is a Hom like this, such that alpha is epsilon prime X which is exactly means that this is the right adjoint. So that's the right adjoint, and this is the end of the proof that what? 4 implies 5. Okay, so now 5 implies 6. So now we have condition that functor I has the right adjoint, and I want to construct a distinguished triangle with a couple of properties. And this is not very hard, right? So since I have this adjunction, I just proceed to construct a distinguished triangle like before. So I have I prime, say M, then there is this map epsilon prime M to the M. So then I can complete this two distinguished triangle, call this object B, then I prime M with a shift. So that's a distinguished triangle. So to this distinguished triangle I apply functor home Ix. So I guess X, yeah, so X of course has to be in the L. So then I'll get home Ix I prime M mapped to the home Ix M mapped to the home Ix B, and then prime Ix I prime M with the shift. Okay, so some of these homes are, well, for example, if I look at the first one, since I is fully faithful, this is the same as the home between X and I prime M, right? And well, the same, yeah, and by the adjunction, right, by the adjunction, since the I prime is the right adjoint, so this map is an isomorphism. And you can of course do the same argument when everything is shifted by 1. So then it means that this next,
Excuse me, where am line?
M in translate category, so M is in the T.
Oh, okay.
Right, so apply this home. So here this isomorphism is the adjunction. Of course, the same will be here, so this map will be the isomorphism. So it means that this home in the middle between Ix and B has to be 0. So this is isomorphic to 0. Or in other words, I can say that the object B is in the right orthogonal to the M. But that's what I want, right? I started with any M, I constructed a distinguished triangle such that this object is in the L, and this column of this map is in the right orthogonal to the M. That's the condition that we have in the 6. So this proves that 5 implies 6, and finally the last proof, 6 implies 1. Okay, let me read the condition what we have in the 6. In the 6 we have a condition that for any object M in the translated category T, we have a distinguished triangle. So there is a distinguished triangle with the N sub M mapped to the M. So I'm going to call this map U sub M. I'm going to call the second map V sub M, and this is to the V sub M. And then there is also W sub M to the N with the index M with the shift by 1. So in this distinguished triangle, N sub M is in the category L, and the B sub M is in the right orthogonal. So suppose we're given a map F from the M to the M prime. So then I'll get two distinguished triangles for M and M prime and the map in the middle. So there is N sub M, M, E sub M, N sub M with the shift. The same for the M prime. So M sub M prime, E sub M prime. So here is a map F, M.
May I ask a question?
Hmm?
Is there a condition for uniqueness in the six?
I'm not assuming anything. I'm assuming that
Yeah,
I have distinguished triangle, and the map between them.
No, you write for any M in tau exists unique
Ah.
distinguished name. So it's not
That's just
insane.
That's just a silly factor. Yeah, but in fact this is unique, so I was right, but I need to prove this. So I want to show that kind of this Vm and Nm are factorial for the M. So in fact we know that this is factorial because, as I was saying, in these six conditions, so we can assume something. We can assume that there is distinguished triangle with the properties. We can assume that there is this functor, or we can assume that there is this functor, and the rest of the data we can just derive. But the moral of the story is that we consider such localizations where you have kind of everything. You have a lot of adjoint functors, and you have a unique distinguished triangle for any object. Okay, so let's proceed. And I want to show, indeed, that there are unique maps on the B's. And to do this, I apply, again, home. So first of all, we can apply home from the M sub M to something to the bottom distinguished triangle. So let me maybe call the distinguished triangle 1 and 2. So apply this home to distinguished triangle 2. So let's see what we get when we apply this. Yeah, I have something shifted. So BM with a shift by -1. So then home N sub M and M prime. So there is prime here. So prime, and this is M prime. So there is a map to the B M prime. So as before, I claim that these two homes are 0. Well, this is because we know the properties of the NM and BM, right? So by the orthogonality, they are 0, so this is an isomorphism. But if this is an isomorphism, I can claim that there is a unique map N sub F from the N prime and F is equal to the F UM. I introduced these names for the maps in the beginning when I stated the condition that we have in the 6. Okay, so on the N there is a unique map which I'm going to call NF. So making this square commutative. Now let me say that similarly you can apply home, but now with a fixed second argument to the VM prime, and apply of course this to the first distinguished triangle. You get exactly the same, all the exact sequence with homes on the in the beginning and the end. You get zeros, you get the isomorphism, and you get the condition that there is a unique. You get the conclusion that there is a unique map N sub F, which is the map between B's. So this is N F should be right. So BM and MM, NM are functorial. So then we define, so we need to define localization to prove one. So we define localization L by the following formulas. So L on the object M, this is by definition object BM, and L on the morphism F, this is B sub F. So, well, some of the things are clear, so I'm not going to check this. So L is additive functor, which is more or less clear from the definition. And also, I think what is clear, that if you apply this L twice, you'll get just the same thing as if you apply L. So, but what is less clear is that L is triangulated functor. And this is what we need to check. Okay.
Maybe we call this model from them to them by another.
Wait,
Yeah, we should. This is supposed to be B sub, yeah. Sorry, this is again. No. Just a mistake on the word. So this is B sub F, of course. Okay, so I want to check, for example, that this commutes with the shifts. To this, I consider two distinguished triangles. So the first one is the n, well, the distinguished triangle that I have, but for the object m shifted by 1. So this is the first distinguished triangle. And the other distinguished triangle is the distinguished triangle for the object M, but I shift this distinguished triangle. So this will be the same M shifted by 1 in the middle, but in other places a little bit different. So here, of course, in the middle, we have the map, which is just the identity. And I don't want to repeat the argument because the argument is exactly the same as before, right? So I'll get a unique map here, right? So, and it is also will be clear that I can use a map in this direction, I can use map in the other direction, so this map will be an isomorphism. So there is a unique isomorphism. So this is an isomorphism. But if this is a unique isomorphism, it means exactly that this functor L commutes with the shifts. So finally, it maps distinguished triangles to distinguished triangles. So take a distinguished triangle, X, Y, Z. So then I can consider the following. I take a distinguished triangle, so this is distinguished triangle in T. I take this distinguished triangle. Now I have a map to the B sub X. I have a map to the B sub Y, and there is the, since this is a functor, there is a reduced map here, which is B sub F. Oh no, well, B for map F, which is a map from X to the Y. I don't want to give names to this map. So this map from the Bx to the By, I can complete to a distinguished triangle and say, let's call this third object C. Okay? So a given distinguished triangle, for X I construct an object, for Y I construct an object, so these are objects Bx and By, and for a map from X to the Y I have a map between Bx and the By. And then I complete this to a distinguished triangle and call this column of the maps from Bx to By object C. Okay. So, yeah, so first of all, the observation is that the C is in the right orthogonal, which is clear since we have a distinguished triangle. Two objects, Bx and By, are in the L right orthogonal, then the C is also in the right orthogonal. So, and argument is more or less the same. So I just apply home to some B prime, which is B prime an object in the right orthogonal.
So first of all, there are two maps. Well, there is an induced map. Maybe let's call this J, which always exists. And then I want to show that this is an isomorphism. Right? But if I want to do this, I can apply this home and I use the 5 lemma. So 5 lemma implies by the argument that we already used several times, I think, that the home from the C to the B prime is isomorphic to the home between Z and B prime. Okay, so then the last step, I look at the distinguished triangle for the Z, so I have NZ, Z, B, Z. And do the same thing. I apply to this distinguished triangle again home into B prime. So since I know that the B with the index Z, this is in the right orthogonal, for the homes from the long exact sequence, I'll get that the home, well, first of all, from the before, home from the C to the B prime, this is isomorphic from the home to the Z, from the Z to the B prime, that's the previous step. Now here, I can also say this is isomorphic to the home from the B sub C to the B prime.
Why did you lie in L? Why did you lies in L?
Well, that is because by assumption in the condition 6, for any object, we have this distinguished triangle with the property that NZ is in the L and BZ is in the L right orthogonal. So you apply this for home B prime, you'll get some vanishing, right? And up vanishing between NZ, which is in the L, and B prime, which is in the right orthogonal. And so this gives you this isomorphism of these homes. So together, you can, you can see that if you combine this together and apply the Unitas lemma for the quotient category, you can conclude.
Why for the quotient, for the L orthogonal?
Yeah, for the subcategory, yes. Then you can conclude that the C by Unitas is isomorphic to the B sub Z, which is what we want, right? We see that distinguished triangles by this functor that we defined functor L are mapped to distinguished triangles. Yeah, and the other is clear. So on the condition that if you apply this twice, you'll get the same as if you apply this once. This is clear. So that's the localization.
What about at X, at that?
Well, it's kind of, if you do this kind of with all possible details, you write this eta, but it's in this case, well, that was a map from the identity functor to the L, right?
Mm-hmm.
But this is kind of given more or less by definition here because we have a distinguished triangle which you prove this functorial, so there is a map here. So it's okay. Yeah, and of course, the last thing that we can check is that if you take the kernel of this localization functor that we constructed, of course, this will be the category L that we are given.
Mm-hmm.
So that's the right localization. Okay.
And I'm sorry, why C is equal to B?
Here? Well, that is because I have this kind of two isomorphisms. I look at the beginning, I look at the end, and apply the Unitas lemma. This is true for any B prime in the L right orthogonal, so by the Unitas lemma for this category, I have this isomorphism. Okay. And by this, more or less by the same proofs, you can prove other statements. I don't want to prove them, so I'm going to formulate them and leave them exercises. So there are two definitions kind of tautological. So a sequence, say tau prime, t prime, t, and t double prime with the functors f and g. So this is a sequence of triangulated categories and triangulated functors. So it's called exact. So if I have three conditions, so E1, so E for exact, so F is fully faithful, E2, G is Grothendieck quotient, and condition 3 is that the image of F is the same as the kernel of G. So this is one definition. Or maybe let me say that I have two parts in the definition, so part 1 and part 2. So part 2 says that this sequence is called localizing if, well, condition L1, so L for localizing, F is fully faithful as before and has right adjoint. I'm going to call this F with the upper shriek. Condition L2, G has fully faithful right adjoint. Right adjoint, G with the upper shriek. And L3 is as before. So this is the same as E3. So this is image of the F is the same as the kernel of the G.
A sequence which is exact is called localizing. I'm confused.
No, well, you can take the again three categories and two functors and postulate these three conditions.
So they
And
are
then you get-
separated.
Then you get localizing. Yes. Yeah. So the conditions are kind of E for the exact and L for the localizing, and they are independent. But of course, well, you see that there are relations.
So the second definition is like split exact.
Yeah, so if you think about the analogy that the first definition gives you the notion of an exact triple in this category of triangulated categories, then the second is something like a splitting exact sequence.
But by the way, we don't in the second definitions we doesn't
Same all the portions.
say that yes that it's with the portions.
Yeah, and that is because I want to give you the exercise.
Is it equivalent?
No, it can be equivalent, of course, but exercise saying that any exact sequence, sorry, any localizing sequence, that way around, any localizing sequence is exact. So this is one exercise. And the second exercise is that if we have a localizing sequence, so then for any object x in the triangulated category T, there is canonical distinguished triangle which is the following. F upper shirt, which is the most standard notation for the right adjoint functor. Now there is the unit of the adjunction, epsilon sub x to the x. Then there is the unit of the adjunction, beta sub x to the g upper shirt g x and the shirt. So this is the second exercise.
Should F and G both have right adjoints? Yeah. There is no technical.
You want this to be a left adjoint?
Yeah, someone.
No. These are both right adjoints because if you go back to the proposition, left adjoint for the embedding of the orthogonal complement.
Yeah.
So essentially, what I'm saying is that if you have, well, the standard situation, this is the say thick type category, this is the quotient. You can say that there is a right adjoint here, or you can say that there is a right adjoint here. These are two equivalent conditions. That's exactly like in a splitting short exact sequences in abelian categories.
That's true.
Okay, so this is the second exercise, and the methods of proving this is, of course, more or less the same as we've done in the proposition. So I think it's really good as an exercise, it's not as the statements that I do on the blackboard. And the last one. The last one is the following, that for an exact sequence, well, the same as before. The following are equivalent. So first condition is that the sequence is localizing. Condition 2 is that the F has a right adjoint. And 3, G is a right adjoint. Okay, so this is all I want to say about the exercise. 3 exercises, not completely trivial, but also not very hard. Okay, so and finally, probably I want to introduce some terminology to finish this section. So, definition, localization, let's say a quotient. So we have, say, C that sits inside D, and then there is a D modulo C. So that's an exact sequence. So it's called Gauss-Field quotient or localization. Well, essentially, if the conditions of the previous proposition are satisfied, well, let me say that if the Q from D to the D mod C, that means the right adjoint. So why Gauss-Field localizations are so interesting and have their own name? Well, because of the condition 3 of the proposition, which says that in this case, the quotient category you can compute as a subcategory, which is just the right orthogonal to the category C, which is of course a very useful statement. Because quotient categories are hard, now the morphisms are just so loose. It's very hard to do some computations with loops. But if you have this condition, you can just continue to work with the same category and just choose a subcategory. So this is why this is useful. And the last remark is that, of course, I've done everything for the localizing categories, and the corresponding theory is called the Boswell quotient. And of course, there is kind of co-Boswell, where you have the same situation, but you have the left adjoint from the quotient. And then this quotient is equivalent to the left orthogonal to the subcategory C. So everything can be dualized. Okay.
Are there interesting examples we have interesting examples of both Boswell quotient and Boswell quotient, or we actually worked on one of them?
Well, yeah, that is possible, and you can find this in the applications sometimes, and this is I think this is the right way to write this word. This is reclamor or recolamor. This is a French word, means gluing, and this is the situation where you have the following: you have C, which is the fourth category in the D, then there is a quotient, and then there are functors like this. So there are both left adjoints and the right adjoints. So if you have this situation, and the Boswell and co-Boswell together, this is called recolamor. And you have such examples a lot in algebraic topology, but a little bit less in algebraic geometry.
But actually, as we'll see examples in algebraic geometry of both Boswell quotient and co-Boswell quotient.
Yes, that's an example. Well, that's how it's called in theory, but you want an example in algebraic geometry?
As we will see both localization and co-localization in examples.
Yeah, for this, there is an example, yes. To answer this question, I'm going to use something. Let me just, for simplicity, do commutative algebra. So you have a derived category of the ring, then you have the derived category of the ring of the I torsion modules. So this is the derived local cohomology. So then this is the right adjoint for the embedding functor. So the left adjoint is just the embedding I, and the right adjoint for the local cohomology, this is the completion functor, so maybe derived. So then the kernel is the OX modules with quasi-coherent cohomology on the complement. So here I can say that X is the, so let me separate this from the general definition. So X is the spec of R, so Z is the vanishing set of I, and the U is the complement. So here what we have, so we call the J, the embedding of this open subset. All right, so then this functor, I guess, is the J upper star, right? So then the left adjoint will be J lower star, and then there's also right adjoint, which is the J with the cross. This is not star, this is cross. So that's an example of recolamor in commutative algebra. If you know something about algebraic topology, you can compare this to algebraic topology, and usually recolamor is switched. But if you try to switch this recolamor, it won't work in algebraic geometry, because in algebraic geometry there is no 6-functor formalism. There's only kind of 4.5 functors.
Yeah, and the standard functor from homology category to derived category is not Boswell.
Yes, and that's the reason why, in general, the derived category doesn't happen. It's not locally small, but it is for Grothendieck abelian categories.
Mm-hmm.
That will be probably in this course.
And we will understand that for Grothendieck abelian category is Boswell or co-Boswell quotient. Or no?
For Grothendieck abelian category, going from the homotopy category to the derived category is a Boswell localization.
Okay, so we will see. And not combustible. No, no. Okay. It's interesting that there's a lot of the notes missing. It's a little bit confusing why I don't have my notes. Okay. Maybe I'll start the next section and continue next time. So that's all I want to say about the crossword localization and localization functors in general. So the next section, I think this is 3.3, and this will be homotopy, limits and colimits in triangulated categories. So I want to separate these topics. There is zero homotopy limits and colimits in any triangulated category, and there are more general homotopy limits and colimits. By the way, I have a question. Have you seen homotopy limits and colimits in some categories?
Topology.
Yeah. What? In what categories?
Can you come up with a category?
Homotopy category what?
Topological spaces.
Okay, so in space, for example. Yeah.
Yes, yes. Something we've seen in the college.
Yeah, so I just want to say that, well, probably historically you can start with something like homotopy category of topological spaces, or maybe better homotopy category of simplicial sets, and define the notion of homotopy limit and colimit. But then I think the theory was developed for the model categories. You can study theory of homotopy limits and colimits in model categories. And kind of in triangulated categories, you can do just a little bit of homotopy limits and colimits, kind of for simplest possible diagrams. So there is no kind of full theory. It's not possible to do full theory of homotopy limits and colimits in triangulated categories. So it will be just very kind of partial definitions and partial results. But it's still useful. Well, one of the main applications for us will be that we prove that using homotopy colimits, we prove that any localizing category is thick, which is just from definition doesn't follow at all. It's kind of non-trivial proof. And when we finish with the simple observations about homotopy limits and colimits that we can do in any triangulated category, the next section will be 3.4, will be homotopy limits and colimits in derived categories. And there you can define homotopy limit and or colimit for just for any filter diagram or any directed diagram, which is much better, and we'll need this theory later for the proofs. Well, but let me indicate maybe the definition, how it is defined, and the definitions I think is quite intuitively clear. You can probably recover this definition if you think about this a little bit. So I assume that T is a triangulated category with countable products. Well, I can assume that I have all products, but the countable products will be enough for what I'm going to do. So given a sequence, which is just a sequence for the
going to define homotopy limit. So this is just a sequence for the limit, which is also called the inverse limit for the inductive system. So we have x3 mapped to x2, x2 maps to x1, and this is mapped to x0. So there are maps which I'm going to call J3, J2, J1. So this is just the simplest possible diagram for directed, for the inverse limit. So then I can define the map mu. This is the map from the product of all the xi's to the product of all the xi's. Well, the products exist because this is just a countable set of objects. And map for the product I can define in terms of the components. So for the product, say, take a product, and I also fix projection. So let's call this pk. This is just the projection. Or maybe it's better to call this index I as before, and the projection to the object with the number k. So if I want to specify this map mu, I can just write what projections or compositions these projections are. So the composition of the pk and mu, this is by definition j, k plus 1, pk. So this defines map mu uniquely. And we can think of this as a matrix. So informally, mu is an infinite matrix.
Isn't it should be just jk?
No, jk plus 1.
But so pk, we stand in xk, and in xk we only have map jk. From xk to xk minus 1.
pk plus 1? Yeah, so the matrix that I want to write, I want to have zeros everywhere. I'm going to write zeros on the diagonal, but above the diagonal I have j1, j2, etc. So the rest are all other entries are 0. And that's an infinite matrix because it's infinite product. Okay, so then the definition of the homotopy limit. So the homotopy limit of the diagram that we have before. So this x3, x2, x1, x0. So is an object in T fitting in the distinguished triangle like this. So we have homotopy. So an object, let's call this whole lim xi. So whole lim xi. So then we have product of the xi's, again product of the xi's, and there's a map between the product, which is just identity, minus the map mu that we just defined. So this is homotopy limit of the xi shifted. Right? So we start with the product, we have a map from product to the product. We can complete this to a distinguished triangle. Well, I'll just do it kind of not to the right but to the left and call this homotopy limit.
It's like a usual limit.
Yeah, it's like a usual theory of the Milner limit, right? So maybe I do this as a remark. So remark. So compare this to the Milner's definition of the limit.
Milner definition is like equalizer products.
Now, in the Milner definition of the limit, you consider the following. You take, for example, an abelian category. So, take diagram abelian category. No, the same diagram as before. So this one. x3, x2, x1, x0, right? And you form the same thing. So you form the product of all these xi's. You consider map 1 minus mu to the product of all the xi's. So, and this map has a kernel and a kernel. Do you know the kernel of the kernel?
The kernel should be the kernel should be
In the abelian category?
Yep.
Yes, of course.
No, let's think about the category of abelian groups. That's enough for the analogy.
well, the kernel should be the limit.
Yeah. So this is the limit of the xi. And what's the colimit? Oh, sorry, the co-kernel. No, this is not the colimit, of course. So what's the co-kernel?
Derived functor.
Yep. So this is R1 applied to the lim xi. So the Milner theory of the derived limits is the following. If you have a very simple diagram like this, then there is only first derived limit. All the higher derived limits are trivial, and you can form a diagram like this. You can compute the limit, or you compute the first derived limit. So in the Milner's theory, it means that you can kind of take this as a definition. So this is the standard definition of the limit, and you take this as a definition of the R1. So then you can ask a question how to show that actually this coincides with the derived functor, but that's a separate proof in the abelian category. So probably not going to do this. Well, maybe next time if I need this for something.
The limit is the same, but we should take the digit sum.
Yeah. For example, if you want to define the
And
homotopical.
also there is a left derived function.
Yes, there is a left derived functor, but usually in the applications it is 0.
Because
Yeah.
these are Grothendieck category.
Yeah, because usually in all our applications, like in modules and the shifts on topological space and the shifts, quasi-coherent shifts, algebraic varieties.
But it is not usually zero.
No, if you take something like even like abelian groups, no, this is not necessarily 0. No.
Mhm. Okay.
And if you have your more complicated diagrams, you have all the other derived functors. So the vanishing of the derived functor starting with the 2, in this case, this follows from the simplicity of the diagram. In general, there are higher derived functors, not just the first
What
one.
is the simplicity?
Hmm?
What is the simplicity?
Well, this is just very simple kind of diagram, which is parameterized.
Bounded from the right.
Explicitly, this is just the for ordered set, which is just natural numbers. Directed set, which is natural numbers, and there are other directed sets. You can take limits over directed sets, and potentially for those limits, you have higher derived limits, not just the first one. But for the first one, this is how this works. For example, in abelian groups and abelian categories, and this is what is generalized in this definition. You can go, as we're saying, the theory of abelian categories is twice as hard as theory of template categories. Because in the abelian category, for morphism, you have kernel and co-kernel. So you kind of need to consider two objects. And they together kind of control the morphism. In the template case, there is only, say, this thing, which is just a cone up to a shift. And this object controls everything. So this whole limb kind of controls limb and this limb together.
So in arbitrary little category, we can develop both derived functors that are both left and right derived functor with one same functor, and it kind of works. I mean,
Yeah, you can take left, for the limits, for example, you have right derived functors, yes.
and left-right functors also can exist. I mean, usually we can take
For the limit?
yeah.
For the well, there are some functors, yes, but it's not less interesting because this is left exact. So this guarantees that the R0 is the same as the functor, but if you have a left-right functor, L0 of this functor will be something different, not the limit. That's the problem. No, this is a standard statement from homological algebra. If you have a left-right functor, take the right-to-right functors of it, then the zeros to right functor is the same as the given.
I'm not saying I was sort of surprised by the fact that you can develop a theory of the right functors for something that is not exact on at least one of the sides.
Well, that is not a problem. You can always have the right functors for any functor, not necessarily exact left on the right. The right functor has nothing to do with left to right exactness. It has to do only with the property that the zeros to right functor coincide with the functor you're given. That's the only thing that's important. But for any functor, well, you can define left and right. And there are examples of the non-exact functors where you can consider left and right the right functor. For example, the completion functor.
Mm-hmm.
Okay, I have a feeling that I'm out of time. But I hope now with this kind of discussion of the Milner's theory of the limits, it's clear why the definition is set up in this way. It's not surprising at all. It's a very natural thing to do. Okay, so we'll continue next week.
Можно спросить, если мы возьмем фиксированный элемент алгебровой теории, их 0, рассмотрим аттракцию производной теории. Вот этот холим, он будет совпадать с гомологией будут лим x итых и r и вторые гомологии r1 и будут?
Я думаю, что я это даже не но когда будет раздел 3.4, потому что 3.3 я чувствую, что это теории.
Хорошо.